Hi, Assalamualaikum. Welcome back to my channel, Physics from 5 KSSM. Today we continue Chapter 5, Electronics, on the first part, 5.1 Electron. In this video, I will discuss two learning standards. The first one, describe thermionic emissions and cathode rays. The second one, describe effects of electric and magnetic fields on cathode rays. Okay, what is thermionic emissions? Watch this video to understand what is the meaning of thermionic emissions. Thermionic emission is a process involving emission of electrons from heated metal surface. You can see below the surface of metal or conductor there are a lot of free electrons. Electrons will just stay there with certain amount of kinetic energy. Once heat is applied, electron will gain enough energy and able to free itself and release from the surface of heated metal. The release of electrons from the surface of heated metal, we call it process of thermionic emissions. An electric current is produced when charged particles, electrons, flow in conductor. Can electron move through a vacuum without a conductor? Can these electrons that release out from the thermionic emissions now pass through a vacuum? Let's watch this one. This is about vacuum tube. The vacuum tube consists of anode, which is connected to positive terminal, cathode connect to negative terminal of power supply, and filament just requires small voltage 6 volt. Filament is heated up. Thermionic emission will cause electrons to be released from the surface of heated metal. Electrons will be attracted to anode and pass through a smaller diameter of anode, or we call it focusing anode. It will produce a beam of electrons that travel in a straight line. The beam of electrons now travel in the vacuum region here. So once the electrons that release or the beam of electrons travel, hit the screen, it will cause some of the kinetic energy of electrons will be converted to light energy, or we call it fluorescence effect. The electrons that release in form of beam of electrons at higher speed, we call it cathode rays. Okay, let's look at activity 5.1. Look at the discussion involved for the activity, which discuss about the use of vacuum tube to show cathode ray travels in vacuum. So look at the first one, E. What is thermionic emission? Thermionic emission is the process of electrons released from the surface of heated metal. What is a function of 6 volt power supply and extra high tension EHT power supply? Just now, in the vacuum tube, the filament is just connected to 6 volt power supply. The cathode and anode is connected to extra high tension EHT power supply that can exceed to 4000 volt. So what are the function of the 6 volt power supply and EHT power supply? The 6 volt power supply is to heat up the filament for thermionic emissions. Filament is placed close to the cathode, so the filaments will heat up the cathode and causes electron to be released out from the surface of cathode. The process involved is thermionic emission. While the EHT power supply is connected across cathode and anode, which provides kinetic energy to electrons, or we can say it produces high speed of cathode rays. Why must the tube be in the state of vacuum? can see just now in vacuum tube, cathode ray travel in vacuum before hit the screen. Can you imagine if this is not vacuum, meaning there are air molecules in this tube? So once the cathode ray pass through this part, it will collide with air particles. So this one will cause some of the energy of cathode rays to be lost. So this vacuum section is for the cathode ray to travel without energy loss. How can cathode rays be produced in vacuum tube? Just now we have observed that electron that release from the thermionic emission at the surface of metal. So what happens to the electrons? Once the filament heats up, it will heat up the cathode, electron will be released out. Because of EHT is on, the electron will be attracted to anode and focused to form a beam of electrons. So the beam of electrons that pass through this vacuum section, we call it cathode rays. Electrons from cathode receive high electric potential energy from EHT power supply and accelerated. Okay, this is how to explain the production of cathode rays in vacuum tube. Let's explain thermionic emission and the production of cathode rays in the vacuum tube using extra high tension power supply. This is a vacuum tube. Let's look at one by one. The first one, the function of the 6-volt power supply is to heat up filament. Next, the function of filament is to heat up cathode to produce thermionic emission at cathode. Next, the EHT power supply is to supply high kinetic energy to cathode rays. Thus, it will produce cathode rays that travel at high speed. So this is the part where we call it vacuum part. For vacuum part, cathode rays travel without energy loss. Okay, let's look at effects of electric field and magnetic field on cathode rays. Thus, cathode ray will show effects when travel in electric field or magnetic field. Cathode rays are beams of electrons moving at high speed in vacuum. The characteristics of cathode rays can be studied using deflection tube and multisplash tube. Let's look at activity 5.2. The aim of this activity is to study the effects of electric field on cathode rays using a deflection tube. Apparatus required: deflection tube, 6-volt power supply, EHT power supply, and connecting wires. As you can see from this diagram, this is the 6-volt power supply that connected to filament. Filament is placed near to the cathode to heat up cathode. And this is anode. You can see cathode and anode is connected to EHT power supply. And in this tube, you can see there are 2 plates. Above plates is connected to positive terminal of EHT power supply. The bottom part of the plate connected to negative terminal of the EHT power supply. Okay, let's try to see what happens when S1 and S2 is closed. Current will flow and the filament will glow and heats up cathode. Because of EHT power supply is on, electrons will be released out from the surface of cathode through thermionic emission. And then the electron will be accelerated toward anodes, focused by anode to form a beam of electron, or we call it cathode rays. If S3 is open, the cathode ray will travel in a straight line. Let's say if S3 is closed. When S3 is closed, the above plate will become positive plate and the bottom one will become negative plate. Thus, there is electric field between positive and negative plate. What happens to cathode rays? Cathode rays will deflect upwards in parabolic path. If we reverse the terminal of EHT power supply here, we can see the cathode ray deflect downward in opposite direction. Okay, let's watch this video to understand better for this situation. Okay, you can observe here, through thermionic emission, electrons will be produced by cathode. EHT power supply is on. Electron will be accelerated and focused by anode to form cathode rays. There's a part we call it grid. It is connected to negative potential. The function of grid is to control number of electrons that pass through focusing anode, meaning to control brightness of the spot produced on the screen. The more the negative the grid here, the more electron being repelled by the grid, thus less electron is allowed to pass through the focusing anode. So less number of cathode rays or less number of electrons allowed, meaning less light energy produced on the screen. So the number of electrons of the cathode rays actually represent the brightness of the light produced on the screen. Okay, let's look at what happens before. If S1 and S2 are turned on, S3 is open, the cathode ray will travel in a straight line. No deflection. When S1, S2 and S3 are turned on, you can see if the above plate is positive, bottom one is negative, cathode ray deflect upwards. If reverse the terminal of EHT, the bottom part positive, the upper part is negative, cathode ray deflect downward. So from this activity, let's try to answer this question. State your observations on the fluorescent grid when S1 and S2 are turned on. Cathode rays accelerated in straight line. S1, S2 turned on, cathode rays deflected upwards towards positive plate in parabolic path. Switches S1, S2, S3 turn on and potential difference of deflection plate is reversed. Cathode rays deflected downwards towards positive plate in parabolic path. So based on this activity, what we can say about properties of cathode ray. Okay, before that, let's look at one more video to observe what happens to electrons when travel in electric field. Does cathode ray deflected by electric field or not? So you can see this is plate. This one will cause the cathode ray to be deflected up or down. Deflection plate, which is Y plate, is connected to the point, we call it Y gain. Okay, for the Y gain, insert one battery meaning there is a potential difference across above and below plate. Let's say above is positive, below is negative. So you can see the cathode ray deflected upwards. So on the screen, you can see the point or the spot that produced on the screen now deflect up. Let's say if reverse the terminal, meaning the above is negative, the bottom is positive. So you can see the cathode ray deflect downwards. The spot produced on the screen also move downwards. If remove the battery, meaning no power supply, there is no electric field between the two plates, you can see the spot will stay at the center of the screen, meaning it travels in a straight line without deflection. So from here, what can you conclude from the video just now? What we can say, cathode rays travel in a straight line. Cathode rays can be deflected by electric field. They are deflected towards positive plate in parabolic path. Cathode rays are negatively charged. As you can see from just now, cathode ray always deflected towards positive plates, meaning cathode rays are negatively charged. Activity 5.3, to study the effects of magnetic field on cathode ray using multisplash tube, apparatus, multisplash tube, 6-volt power supply, EHT power supply, bar magnet, and connecting wires. So this diagram shows a multisplash tube. So you can see from here the filament part, which is connected to 6-volt power supply, and there's a switch S1. Cathode and anode is connected to EHT power supply, and there's a switch S2. In the vacuum here, you can see there is a multi-cross, which is also connected to EHT power supply. And here we have a screen, fluorescent screen. So it's coated with fluorescent material. In this activity, we want to discuss how cathode rays is affected by magnetic field, which is what happens to the cathode rays when we bring a bar magnet towards the vacuum tube. Watch this video. So this is a multi-cross tube that connected to EHT power supply, very high voltage power supply, 2000 to 4000 kilovolt, 2000 to 4000 volt. So this is a multi-cross. When this S1 is turned on, you can see a shadow surrounded by yellowish color, means the shadow is formed by filament, or showing that light travel in a straight line. Then we turn on S2. You can see there's a shadow formed on the screen, but now surrounded by green color. You can see the green light is caused by fluorescent effects when cathode ray hits the screen. So when we bring the magnet near to the vacuum tube, we can see the image of the multi-cross is distorted and deflected. So what caused this situation? We want to discuss further on this part. Let's look at discussion for this activity. Number 1, state your observation of the shadow form on the fluorescent screen when switch S1 is turned on. You can see a shadow of multi-cross form on the screen because light travels in a straight line. So you can see a shadow of multi-cross form on the screen with a yellowish color surrounded it. So the color is caused by light from the filament. B. Switches S1 and S2 are turned on. The shadow of multi-cross becomes darker with green light around it. The green light is caused by kinetic energy of the electrons that converts to light energy, okay, due to fluorescent effect. Switches S1 and S2 are turned on, and the north pole of magnet is brought to the side of multi-cross tube. Two shadows are seen on the screen. The shadow cast by light, thus affected by magnet, stays at the center. The shadow cast by cathode rays will be distorted and deflected. As you observe in the video just now, you can see the image of multi-cross being distorted and deflected. Explain your observation when the north pole of magnet is brought to the right side of the multi-cross tube. Let's say this situation. This is a multi-cross shadow that forms on the screen. We bring the bar magnet north pole to the right of the vacuum tube. Which direction the multi-cross will be, or the multi-cross shadow will be deflected? For this one, we can apply Fleming's left-hand rule. Direction shown by the thumb is direction of force or motion. In this case, represent direction of deflection for the cathode rays. The field always north to south, meaning your four fingers always pointing to south. And then the center finger represent current. In this case, this is not current but cathode rays. Cathode rays actually is electrons, which is negatively charged. Thus, if you apply this finger, middle finger, so you must place this finger opposite to the direction of cathode rays moving. So in this case, if you apply the Fleming's left-hand rule, you can find that direction of deflection is upwards. The shadow deflected up because cathode rays is negatively charged. Direction of deflection is determined by Fleming's left-hand rule. Okay, let's look at this one, some explanation regarding the activity carried out. When S1 is turned on, light from the tungsten filament is blocked by an opaque object which is multi-cross to form a shadow. Light travels in a straight line, so you can see a shadow with yellowish color around it. S1 and S2 turn on, cathode rays are blocked by multi-cross to form a shadow. Cathode rays travel in a straight line. Cathode rays also produce fluorescent effects on the screen surrounding the shadow. This shows that cathode rays possess momentum and kinetic energy. The fluorescent effects produce green light, which shows that kinetic energy of cathode rays is converted to light energy. S1 and S2 are turned on and magnet is placed near the tube. One shadow is due to light formed from the hot tungsten filament, stays at the center. The other shadow is due to deflection of the cathode ray by bar magnet, is placed near the tube. Deflection of cathode rays can be determined by Fleming's left-hand rule. So in this case, you can see this is the screen. So you place your forefinger pointing to south, meaning north to south. You put your forefinger direction to the right. direction of the middle finger, which is represent current, is into the screen, opposite to direction of cathode rays. And then your thumb represent direction of deflection of the shadow, which is downwards. So this is how we determine. You can try yourself to determine direction of deflection for the multi-cross shadow. From this activity, we can see that the cathode ray shows deflection when placed in magnetic field. So from here, we can conclude the properties of cathode ray is it can be deflected by magnetic field. In the previous activity, we have proved that properties of cathode rays are cathode rays is negatively charged and deflected by electric field. So now we have three properties that we can get from this activity. The first one is cathode rays is negatively charged because it is electrons. The second one, it can be deflected by electric field. The third one, cathode rays also can be deflected by magnetic field. Alright, let's look at the next part, potential difference across cathode and anode. We have discussed before, if EHT power supply is off, there will be no potential difference between cathode and anode. Electrons that release through thermionic emissions just stay near the surface of cathode here. When EHT power supply is on, there is potential difference between cathode and anode. Velocity of an electron in cathode ray tube we can determine. Figure shows the formation of cathode rays in a vacuum tube. The electrical potential energy E of electron is given by E equals to EV. E is electrical potential energy. E equals to charge of an electron. V is voltage or potential difference between cathode and anode. The charge of an electron is 1.6 times 10 to the power of negative 19 coulomb. If you still remember the formula here, this is the formula that we discussed in the topic of potential difference. E equals to QV, where Q is quantity of charge, V is voltage. In this case, we just discussed about velocity or potential difference supplied to one electron. Thus, electrical potential energy of one electron is equals to EV, where E, the small e, is charge of one electron. So capital E here is electrical potential energy for one electron. Applying the principle of conservation of energy, electrical potential energy of an electron is equals to maximum kinetic energy of an electron. Thus we get EV equals to half mv squared max, where E is charge of an electron, capital V potential difference between cathode and anode, or voltage of EHT, M is mass of an electron, Vmax is maximum velocity of an electron. Charge of an electron is 1.6 times 10 to the power negative 19 coulomb, and mass of an electron is 9.11 times 10 to the power negative 31 kilogram. No need to memorize all this value. This one will be given to you. Let's look at example. Example 1. Figure 5.5 shows electron beam that is accelerated from cathode to anode in a vacuum. Potential difference across cathode and anode is 550 volts. Mass of electron is given. Charge of an electron is also given. What is electrical potential energy of an electron? Remember the formula. Electrical potential energy of an electron equals to charge of one electron multiply voltage of EHT, or voltage across cathode and anode. So we get 1.6 times 10 to the power negative 19 times 550. Thus we get 8.8 times 10 to the power of negative 17 joule. Next, what is kinetic energy of an electron when it reaches at the anode? Applying principle of conservation of energy, kinetic energy of an electron is equals to electrical potential energy of electron. Thus we get the same value as this one, 8.8 times 10 to the power of negative 17 joule. See, what is maximum velocity of an electron when it reaches an anode? Again, apply principle of conservation of energy. Electrical potential energy of an electron is equals to kinetic energy gained by an electron. So we have this one, half mv squared equals to EV. Thus V equals to square root of 2 EV divided by m. We just substitute the value of EV. EV already calculated here. 8.8 times 10 to the power negative 17 divided by mass of an electron, that given here. So you calculate, you will get maximum velocity of an electron is equals to 1.39 times 10 to the power 7 meter second to the power negative 1. So this value of velocity represent velocity of the cathode rays. Okay, that's all my video today. I will continue in my next video, Formative Practice 5.1. Thank you for watching. Bye.